Okay, let's get started with the last session of the day. Welcome. First, we have Arkadiusz and Joost talking about incident management. And they like me to stress that they are not bankers, but they work for a bank that needs to have incident management, and they will let us know more about the details. All yours.
Hello, thank you for coming. This almost the last talk this afternoon and the series of the conference. Let us talk about the incident management. As it was said, we are working in ING. ING is one of the leading bank in Europe. However, we are not per se working the bank. So we are working in ING Tech, which is a IT tech company that has only one client, the ING Bank. So whenever we do always thinking about the bank and the customers. The ING has 40 million of customers. ING itself has 60,000 of employees, where 20,000 of them are in the ING Tech. So ING has branches all over the world in 40 countries, including, of course, the Netherlands, where is the headquarters, but also in Spain, Germany, Poland, Romania, Philippines, and the US. So as it was mentioned, we will be talking about the incident management using a HOX process. However, we will start with other Tech AIOps project that we are also developing in ING. Few words about us. So I'm Arek, and I am in ING for last 3 years. I am a leading product lead of AIOps team. Previously, I was working in academia, especially in high energy physics domain. And Joost?
Yeah, so my name is Joost. I'm a master student at the TU Delft, and I'm currently conducting my master thesis at the AI for FinTech Lab at ING, which is a collaboration between Delft University and ING. So I'm conducting this project for a year now, so I'm almost finalizing. I'm finalizing it right now, and yeah, I'm doing this for the joint degree of Applied Mathematics and Computer Science. So I also added some of the contact details. We will share the presentation later, so feel free to reach out.
So I have mentioned about AIOps. So what is AIOps? This is a relatively new term that was proposed in 2016, and AIOps combines big data and machine learning to automate IT operation processes, including event correlation, anomaly detection, and causality determination. So what are the IT operations? This is the set of all processes and services that are provided and provisioned by any IT staff run a business. Operation work can include responding to the tickets generation for maintenance work or customer issues. Very often, AIOps can be mislead with DevOps. So, however, it's something different. DevOps is a set of practice and tools that integrates and automates the work of software development and IT operations. So, we in AIOps very often use DevOps techniques. We closely collaborate with DevOps engineers, but we are still a data scientist. However, as a data scientist, we are dealing with very narrow scope of the data. The data are always related to IT systems. You can think about the virtual machine or the containers. And especially, we are dealing with the time series, so matrices like CPU utilization, memory or network input-output. We can also observe the relation between the different components, the asset, like two virtual machines can send some messages and then we are tracking down these messages. So this is a network tracing. We can also observe the machine itself, looking at the logs. Especially, we can look at the events, which could be think of like a warning logs, and the incidents. So the incidents are the situation when the machine is really broken, so it's turned off or the network is down. So in that cases, sometimes the incident is raised automatically, sometimes it is raised by a human. And Jos will be talking in a minute about the relation between the events, so these warnings, and the incidents. But we are also developing other models based on this data. One of them is a capacity management. So you can think about the forecasting. So in this case, we can look at the cluster of the servers. And in this cluster, each server has some unit of, for instance, CPU. Then we can sum up this limit, and this is the orange line. And we can look at the utilization of these servers, and these are the black dots. And then we can try to forecast what will be the usage of this cluster in the future for the next 30, 60, 90 days. Why we are interested in that? Because we always have to provision the enough CPU power for our consumers. And installing a new server is a quite demanding stuff. So first of all, you have to collect the signature from the old management. Then you have to place the order. Then the order has to be shipped. Then someone has to check the server. Then the software has to be installed, and then it has to be integrated with the system. So that usually takes around 2 to 3 months. So of course, we can make it this in advance and just order the servers way before, but then we are losing money because the servers are not used. So our goal is to shrink that gap here, so that always we will demand the new servers to the limit that is needed. Another example is anomaly detection. So you can think of near real-time detection when we have a system. For instance, again, you can think about the CPU utilization. And if the machine is working, it's registering the metrics. So this is a blue line. And based on the history, last few months, we can predict what should be the utilization at that particular moment. And this is a green line. And of course, with some confidential band, and this is the greenish area. And when the CPU is detected higher or lower, since we are having a band that is also limited from below, we can raise some warnings to the operations. I have mentioned about the virtual machine. So virtual machine, in the moment of deploying, usually you have to precise how many CPU you will be using, how many memory. For instance, 8 units of the CPU and 32 gigabytes of memory. However, after some time, it could turn out that you need only 5 CPU and you need only 16 of RAM. And then we have created, in collaboration with the subject matter expert, the recommendation system. So if the machine is configured correctly, then okay. But if not, we are sending the recommendation to management team to downsize, to consider downsizing of such a machine. In the critical situation, we can even consider or suggest decommissioning of such a machine. All that can help in creating like an umbrella over all products that we are creating when the system is observed. And then with our tools, we are observing each component of the machine. And if something is wrong is happening, there we are sending the message that triggered the alert, and the operator, so the human, is getting the phone call, SMS, or other way is getting the information, and then the person is going directly to the machine to check if everything is fine. So our goal aim is to have the prediction that for the next 4 hours everything will be fine, and if something is warning, the operator will have at least 4 hours to prevent from the critical error, so downsize. And this is what one approach is made by Joost. So Joost?
Yeah, hi. So I will talk a little bit about the Hogs process that we used and what the results were in practice. So first of all, what setting are we talking? So we're talking about discrete occurrences in continuous time. And so what are discrete occurrences in continuous time, for example? These are, for instance, the IT arrivals, or financial orders, or earthquakes. There's a large range of things that are discrete in continuous time. So maybe to give an example of what is not a discrete arrival in continuous time, there are time series. They have continuous values in continuous time. So that's the setting we're working in. And then I will start off with a few definitions that we need to establish. So first of all, we're interested at a certain point in time, how many of these discrete occurrences have we seen? So we will denote that NT. So that will be an integer, how many of these occurrences have we seen at this certain time? And then subsequently, we want to know how many of these occurrences have occurred within this really small time interval. So we will denote this this way. And now the key focus for us is at a certain point in time, we want to know what's the probability that an occurrence is going to happen in this really small time interval, so t until dt, given it hasn't happened before yet. So this comes down to something called the intensity function, and this is really aligned with, for the talk on survivor analysis that has been given already, to the hazard rate. The only difference is that in our case, this is conditional upon history. So whereas the hazard rate is not conditional upon history, we do actually have this relation. So this is a crucial function that we will utilize throughout the rest of the talk, where we say, okay, what's the infinitesimal probability that we will see this arrival in this small time interval given the history? So the most simple of point processes that are there are Poisson processes, and I think you've probably heard once or regarding the Poisson distribution, Poisson processes. So the whole thing there is that this intensity is actually a constant, so it's not dependent on the history and not dependent on time. Therefore we have a memoryless property, and what we see is that actually over time the intensity, so this infinitesimal probability of an arrival, does not change. So it's independent of time and independent of history. However, what we saw for IT arrivals at ING, this is not at all the case. So they are definitely dependent upon time. So they obey working hours, basically. So during the weekends and after working hours, there are way less of these outages. So definitely we need to have an intensity function which is dependent upon time. This is not that difficult. We can transform the intensity, the constant intensity, to an intensity function. However, in that case, we still don't incorporate the history. And what we see is that actually, once we observe certain arrivals, certain occurrences, we trigger subsequent occurrences. So we increase this infinitesimal probability, actually. And therefore, we refrain to Hogs processes, which are actually able to incorporate this. So what we see, we once again have this constant baseline, really. However, we sum over all prior arrivals that we've seen before, and we assign an additional incremental infinitesimal probability to show that we have a higher probability of seeing a subsequent arrival, which we do by means of a memory kernel. So this is a function which decays over time, and once we see an arrival, we get an increase in this infinitesimal probability. And yeah, so at a certain point of time, we sum over all prior arrivals and see how much decay is basically left over time, which results really in this zigzagging behavior. However, yeah, we need to enforce that this function is decreasing over time, which is of course really logical. So once we see an arrival, it increases the probability, but as long as it doesn't have, it decays over time. So now we have two observations. Well, it's time dependent, and most important, it's dependent upon history, and that's really important for our case. So by using this using this memory kernel, yeah, we could enforce this. However, what we now have is only one process, really. So we assume only one point process. However, what we actually see at ING is that we have many of these different, well, we mentioned these warnings. So there are many different types of warnings, and we have many of these different outages. So it doesn't make sense to throw this all on one pile, and we really need to distinguish between the different discrete occurrences in continuous time. So we do not have one type, we have, well, different types, different point processes. And then if we take, for example, 5 of these, we can really see that we build up these 5 different point processes. And if we think about this in the context of these IT arrivals that we've seen, we could, for instance, imagine that we have these green circles that are events of a certain type, and that we have these brown squares that are incidents. And we see, well, after these circles happen, we often see these squares happen. So how can we put this into a mathematical framework and test this really? So what we now do is we had this Hawks process, this univariate Hawks process, we transform it to this marked Hawks process, which is nothing more than just a multivariate process. But for each dimension, we say this is a mark. So for each mark, what we do, we give them a baseline, which we saw from the Poisson processes, and we sum over all prior arrivals that we've seen, of any type. And then for each of these arrivals, we see, okay, from which type was this actually? And then we have a memory kernel, which covers this behavior that we see, this added behavior, depending on the interrelation between these two different types that we have. So what we see, what's really, really common here in literature is to use an exponential kernel here, because it really gives this zigzagging behavior that we want, and it has super nice properties in computation. From there on, we try to apply this on our work, see how we can utilize this. And one simplification assumption that we used here is that this tau, this decay, that we say, okay, that's not that relation is not dependent on between which types we're actually operating. We say that that's actually constant. So that's the same for all of those. But what's really important, we don't assume this for this instantaneous increase. So this alpha is really this instantaneous increase, and this tau is this decaying behavior. And it's really important that for this alpha, we don't assume this, because this is how much it triggers the other event. So we really want to see how much is this actually. And then to put this all in a causal framework, the general consensus here is to use granular causality. And this granular causality says, okay, so one point process causes another point process if their instantaneous increase, so this alpha parameter in the kernel, if that is not 0. So if we see like an increase, so because if it's 0, it doesn't change anything to the intensity of that process. So basically, uncovering the whole causal structure here comes down to estimating all of these alpha parameters. So what we do is, we need to estimate basically that matrix, and for that it's also important to note that this is not a symmetric relation. So one type of process can trigger another type of process, but doesn't mean that process, once again, triggered the original process. So yeah, basically our whole problem comes down to estimating an excitation matrix. But yeah, the key question that is still there, what do we assume for these marks, for these types that we really have there? So at first, what we tried was a naive approach, was to see, okay, all the messages that we have that come in, we cluster them. So we cluster them in similar messages that kind of come in. So what we did, we pre-processed them, removed some ING jargon there, vectorized them, reduced the dimension because the corpus was quite large, and then we clustered them. Okay, so we have this layer of message clusters. Tried the results out, and we saw it was pretty poor actually. So then we had some brainstorming sessions, thought about this, and what we forgot to incorporate here is that, so we have this type of event, this type of warning, and this type of incident, this outage. However, they seem to have different behavior when they are on the same application as in contrast to other applications. Doesn't mean they can trigger each other, but it's very likely that they have different values for this triggering value. So we build up a whole hierarchy here. So one of these is adding, well, what's actually the monitoring type? Is it an event, is it an incident? But the other three layers, these are really the software layers. So on what server did it happen? On what application did it happen? On what separated area, which is a separated part of the bank, so for instance, a country, did this happen? So, well, the results, we could build up these marks, these types, which are these 5-level layers now. So instead of just a cluster, we assign them all of these 5. We can build that up, and then we utilized a very, very nice library. It's called Tech. It's open source. Definitely check it out. It's really helpful. They have lots of solvers, a lot of different problems that you can overcome with it. And yeah, that helped us build this excitation matrix. And there we have basically all these different types. What is the value that they trigger each other? And what we then did, so we could distinguish between events and incidents. And in here we see, which events, how large is this infinitesimal probability, in increase on an incident. But interestingly enough, we also see like incidents triggering events. So once maybe an incident has happened, outage has happened, it generates additional warning messages. Okay, cool. So what? How can we now use this? We can use this in two approaches. So one is as a predictive tool and one as a post-mortem tool. So as a predictive tool, we say, okay, we get this event message. What event message did we see? Trigger it most often and give that to system engineers. Say, hey, this event is here now. We see it triggered this a lot of times. So that's the one side of the application. And the other one is more post-mortem. So what I said, we had these applications and these servers, and we can actually distinguish them between the different levels. And we can do something a little bit more sophisticated than just averaging over these applications. We can use multi-level modeling here. I won't spend time on that. It requires a whole lecture on its own, but just keep in mind it's a little bit more sophisticated than just averaging. So for the application level, we could see, hey, what applications seem to have similar triggering effect? And we can group them together. And for instance, to a certain team, we can say, hey, if you want to assign people on surveilling different applications, I would recommend putting these together for this guy to kind of, because it seems to be having similar triggering effects on other applications. So hey, then you have this closed scope basically. And of course also do the same for the servers, where we see like 2 servers triggering each other. Very interesting to see what are these servers. Does it make sense that they trigger each other? So that are basically the 2 results that we had so far. And yeah, so what's there now next? So we basically had 2 things to do. So one is validating this. So we want to say, for instance, with these 2 servers, we want to speak with people from this area, say, hey, we found this. Does it make any sense to you? Can you do anything with it? And secondly, we want to deploy it, so put it into production. So that's basically what we got out of the project so far, and that's how far we came. So, any questions? Yeah. Oh.
Thank you for the presentation. So how do you exactly compute the values of this matrix?
So that's so this one. So they use the maximum likelihood-based approach.
Okay.
So you try to maximize the maximum likelihood here. And what you want, so you want to prevent these really small values. So you can, because then it would actually rank across each other. Plus, you need to sum over all these events. So you want to these occurrences. So you want to drop out a lot of them. So you can enforce sparsity here by means of regularization. So what you then do,
Okay, and can you tell how many events are you processing with this method? Or is it potential?
So the thing is, you have these business areas, and you do this per business area. So you can split them into all these different areas, and from there on, it's really depending on how many arrivals you have there. So we looked at 2 years of data there, and then it varies a lot. So there was. So what you see here is at least so the number of different clusters, so number of different types. This area was around 2,000 that you saw.
Okay.
So, but that is just the number of clusters, and yeah.
Okay, thank you.
Thank you. Could you elaborate or explain a bit again why you chose the same decay time for all processes, like the same tau, and why not fit them individually?
Yeah, so especially because when we don't, we arrive at a case where we have non-convex optimization, which becomes pretty tricky. So that's one of those the cases. The other one is, we saw it's really common in literature as well. And we do see there sensitivity in there to what to choose there. So what we did is establish one value that corresponds to, so we kind of looked after how many hours do we say we have less than 1%, or we kind of assume there's less than 1% of excitation left, because we have this exponential decaying vector. And then we established, okay, for 24 hours approximately, we don't think they will trigger each other anymore. And we thought, so we had some talks with some system engineers, and they said, you can kind of generalize this. There will be some areas where this will maybe be different, so we can tune it per area, but you can make this assumption. So that's kind of where we rely upon. But really the core idea why we did it, because it comes down to non-convex optimization. So we kind of had to really.
Okay, so you tune it as a hyperparameter?
Yeah.
Oh, okay, cool, yeah. Thanks.
Which would be really difficult if we would assume for each of these 2,000 different ones to have one. So you can like simplify it also maybe to have it on clusters or something. There is maybe something to explore that's less extreme than for everything the same. But yeah, for now we establish this way. Yeah.
Thanks for the presentation. You mentioned you wanted to have a model where the intensity function depends on the time of the day. Did we see this in the formula then for the final model that you built?
Yeah, so by using the history, you always use the time, because you say, so in here, so you sum over how long ago it is, basically, how long ago the arrival is. So therefore you always use time. So once you use history, you always use time, basically.
Yeah, okay, thanks.
Yeah, okay, but good question.
Okay, thank you very much. I think time is up. We had a signal. Thank you very much for a very interesting talk.
Yeah.